be going through the exam exercise for the homework for that I gave you. Okay, I'll show you exactly in detail how to run the baseline program. Okay, how to save the agents, how to run the save the agent, get the results, how to plot the results, everything. Okay, so let's start. Okay, so first open the script for the MATLAB code that you have and open the Simulink file. These two things, right? So you see, this is your MATLAB window. Okay. This is your MATLAB window. On your left, you will see something called a current folder. Okay. It is very important that you have your MATLAB code and Simulink file in that current folder before you run. Okay. One. Second thing, on your right, well, the positioning may vary based on how you customize your MATLAB, but this is the default setting in MATLAB. Okay. On the right, you have something called workspace. Okay. This is the list of all active variables or functions or uh, anything, matrices, parameters, all those things will be initialized here. Okay. If that value is numerically available here in the workspace, then it is available to everything in MATLAB and Simulink. Okay. Say simple gravity. Okay. Say there is somewhere here, you see gravity, G is equal to 9.81, right? Now, if this is not initialized and you have used G somewhere else, you will get an error. Okay. Why? Because it is not available in the workspace. So done. Now you know the current folder and the workspace. Okay. This itself, this area is the area of the script where you actually have the code written. Okay. And this window, command window here, is where you type in the commands that you want. Okay. Clear up until this point? Now this is the Simulink file. Okay. So here you see that there is a shaded area. This shaded area is for the plant itself, which in this case is the UAV dynamics. Okay, altitude dynamics to be precise. Okay, this block is your RL agent block. This shaded area is your reward function formulation. This is your reference command. Reference value. Okay. This is the error in Z position that you will be using for different purposes. Okay. So till this point, it is basically, this is the plant. Okay. This is the plant, which will equations of motion, that is, which is derived from the equations of motion from a simplified quadrotor altitude system. Okay. This output is Z double dot, which is the acceleration in Z. Okay. That passes through the integrator and you get Z dot, which is also the velocity. Okay. Finally, this passes through another integrator and then you get Z, which is the actual altitude, the Z position. Okay. Now here you will notice that the error signal that is going into this controller, it's simply a proportional controller in this case. Okay. That's why you have only one term, KV. So it's a proportional controller. Okay. And mind you, the controller is for the velocity. Hence, this system is a velocity control system. Okay. Your RL agent, the action that it is being generated is the velocity, reference velocity command. Okay. That is Z dot underscore reference. Okay. And then you have the actual Z coming from here, coming from the system. It's Z dot, sorry, coming from the system, which passes through the error and then goes through this block, which is also the, can be considered a proportional controller, a P controller, right? And then you have the plant dynamics, obviously. These plant dynamics, this is the aerodynamic effect, this is the thrust force, everything comes together. Then you take it over M, which means that you're taking basically specific thrust. And then again, Z double dot, Z dot, Z. Okay. So clear till this point? I really want participation today. 100% clear? Okay, good. Now you want to actually achieve what is it, the final velocity that you're concerned about, or the final position that is your concern position, right? So here you need to have a reference value. Okay, your reference value, in this case, I'll explain you why this is this way. Basically, it's a constant block, okay? Implying you will define a final altitude which you want to reach, for which the RL agent will generate specific set of actions which happen to be the Z velocity. Okay, so you take your actual position and your reference position, out of which you get the output as the error in Z, which is the error in the actual position and desired position. Okay. Now you have this RL agent block, right? In MATLAB, it's a very beautifully laid out block which clearly states everything. So this is the action, which is the output. Input is observation, reward, and is done. Okay, is done is basically the terminal condition. When do you want to terminate? What condition do you want to ensure at the termination of every training episode? Okay. Yes, here there is no termination. We'll come to it. Okay. So observation, you see, we put a mux block here, okay, which takes in two different variables. In this case, it is the reference, the error in position, EZ, and the actual velocity Z dot coming from the system, or velocity Z. See? So these two, now they form a vector and they become the observation space of the RL agent. Okay? Clear? Good. Now, before reward function, you have this is done function. Okay, is done function is basically a binary input that you have to give either 1 or 0. Okay, if you define a function explicitly, what it does is it will, based on the condition satisfaction, it will either give you 0 or 1. Okay, but in this case, we want to make sure that we do not terminate the episode for the entire training steps, right? So we want uniformity in the training steps. So that means every episode will have the same number of steps. Okay. No terminal condition, basically. That's why you see it is connected to a 0 here. It will terminate only when it completes all the steps in that episode. Okay. This is super important. Okay. Whatever we studied, just a minute, whatever we studied up until this point, this is the implementation and practicality of it. So you need to make sure that you fully understand this part. At any point in this class, you do not understand even the simplest of things, please stop me and ask what you want to do or what is not clear. Yes, Yad. Absolutely. Yes. You don't have if go one. Okay, so I mean yes, yes, basically you can have a comparison operator here. Okay. Okay, here you have distance to obstacle. Okay, which is mathematically actual distance minus distance, the absolute position of the obstacle. Okay. This distance, if it is less than a certain threshold distance, okay, if it is less than a certain threshold distance, this will become right here. So less than, say, a constant k. Okay, this is very fundamental. If this condition is true, the output will be 1. If this condition is false, the output will be 0. Okay, so the episode will run till the output of this block is 0. When it becomes 1, that episode terminates. It becomes from 0 to 1. That is, yes, now it is done. So terminate. Clear? Yes, because the condition here is when it is satisfied, forcing it to be 0, right? We could control output will decide whether it is 1 or 0. Okay? But basically the input of that should be binary, 0 or 1 only. Okay? Reward observation can be any vector or anything. And now reward function. Okay? So what is your reward function here? It takes in the error in position. Yes. You have error in position squared. You have velocity squared. And you have another term for making sure that it stops at the end. Okay, this term is EZ times the, okay, can you dictate? Okay, so here you have the actual position, sorry, the error position, you're squaring it. Why? Because of the sign, yes, you want to eliminate the sign, so you will get the curve like this for the for this thing. Okay, and here we can make sure that it is always positive, because here we will sum everything into a negative. Okay, individually you can keep it plus as such. Okay? Then you have this term coming from the reference velocity. Okay, again reference velocity square it, so you get a curve like this. Okay, you are eliminating the sign. Yes.
So basically, all the rewards part there are basically penalties.
Yes, yes, yes. All of them are penalties. So that's why you see plus, and this block is minus basically. So when it is going into the actual reward input of the rlation block, it will all be minus.
So in this case, our best reward is 0.
Best reward is 0, yes. But no, it's less than 0 actually, best reward. Because there will be an definite time. It's not an instantaneous process, right? There is some sort of physical system that needs to move from one place to another. So the best one will be somewhere just less than 0, but negative value.
Why would you analyze with the changes or
the changes? So that way you make sure that the changes are not drastic between the velocities.
So what's the difference when we have the tools adjusted the written in the blackboard, the tools adjusted the words?
Okay.
I felt like I'm doing it again.
Honestly, that are just some examples for you to ponder upon.
Yes.
If you have some different things, you can do that. I didn't want to list exactly what you should do so that you intuitively build a reward function. I wanted you to do. Thank you. The baseline case I'll do you for sure, because I want to show you how to use this MATLAB interface for RL training. Okay. Okay. So going back to this thing now. Okay. So you first initialize all the parameters. Okay. When you initialize the parameters and you refresh this, this red error will go. Okay. It will remain for RL agent, however, because we haven't initialized the RL agent yet. How long is it taking to train for you people generally, the baseline case? Less than half an hour. Yes. Okay, just a minute. No, I'll come to it. Okay, let it initialize. Till that time, I'll explain the code. Okay, so here now you define. Now you define the Simulink file that you have. Okay, whatever Simulink file that you have. Here, because you have continuous observation and action spaces, you use something called RL numeric spec. Okay, this is basically a syntax thing given by MATLAB. Okay, this things up until this point is similar for all algorithms, no matter what you're using, DDPG, PPO, anything you use, this part will remain the same. Okay. It ensures that you have continuous observation space. The other is RL discrete spec, I think. I forgot the other one, but that will give you discrete values only. Now here it will consider all the continuous values for the observation. Okay. And then you have action space. Similarly, even for action space, we will take numeric spec because we want continuous actions. Okay. Here, what we are doing is we are assuming that the lower limit and upper limit for the position and velocity is minus infinity to infinity. Okay. However, that is not a very good way. If you know that your physical system cannot go beyond a certain velocity, put a 5% margin or 10% margin and use that value. Simply because you will reduce the computational burden on it. Then you will have a smaller space to search for, right? So this is not a very good way, putting minus infinity and infinity. Here, now I defined Vmax as 3 meters per second. Okay. So that means the maximum velocity my drone can go in the upward direction is 3 meters per second. So again, for numerical spec, you will define the lower limit and upper limit. Okay. Here, mind you that this is a 2x1 vector, right? So you have two observations. That's why you have a vector of 2x1 here for lower limit and upper limit. However, the action space is only one by one. That is, it's a scalar quantity, one number only. So you can simply define it without a vector. So your lower limit is minus of Vmax. Your upper limit is plus Vmax. Okay. Now, where do you want it to connect? rlSimulink environment, right? You can have either a MATLAB environment or a Simulink environment. A MATLAB environment will simply be a script of the dynamics of the system, right? Here, because you have a Simulink model, you're trying to connect it that way. rlSimulink environment. Okay. And which is, you have to specify the RL agent block here. You see, by default, the name is RL underscore agent, or sorry, RL space agent. Okay. So you can define it that way, RL underscore agent. If you want to keep something else, you change that name here. Okay. Okay. And you pass the observation info and action info into the Simulink environment. And this is a reset function, which will simply make sure that after every episode, your system resets to whatever default that you have. Okay. Otherwise, imagine the training starting from the ending point of the previous episode. That will be very inefficient. Okay. Okay. Now, this is something particular for the DDPG agent. Okay. In the sense that the way the structure is defined. Okay. Say if you have TD3, you will have two critique networks, right? Whereas DDPG, you'll have, okay, you have two, there you'll have three, sorry. Okay. So here you will define what inputs do you want, what outputs do you want, how many neurons do you want per layer, how many layers, what are the activation function per each layer, all those things, right? This is basically a template in MATLAB. You don't have to worry about changing anything here. If you want to change, you change it here. No, not even this. This one. This is where you change the number of neurons, right? This 64 will become 32 or 128 or 512 or whatever you want. And you just simply copy paste this thing, connected layer and ReLU. This combination, this pair that you have here, you will copy and paste it for as many layers as you want. Okay. Now here we have two layers. That is why you will see fully connected ReLU, fully connected ReLU. Okay. The output you see here is 1. And for critique, it will all, yes. Yes. Yes, but it will increase the computation time as well. So the training time will increase. That's what you can try if you want, honestly. Okay. There is no hard and fast rule that I can specify that no, if you increase, the performance will increase or performance will decrease. No, there's no hard and fast rule like that. No theoretical proof for that. Okay. That is simply a thing that you have to empirically find out. Trial and error, basically. Okay. Sorry.
Depends on the situation.
It depends on the situation, right? So output of the critique layer will always be one neuron only. Why? Critique, yes. Yes, because it is the Q value, which is a single scalar value, number, right? So your critique will always have 1. Okay. Actor will have output depending on the system, the number of system actions that you want, depending on the dimensionality of the action space. Okay. In this case, how many actions do you have? 1. So your output of the actor will be 1 only. Again, these are MATLAB defined ways of MATLAB defined template for defining the critique layer and the actor layer again. Okay. Okay. Actor layer again, you have 2 inputs because you have the observation space is 2, right? And here in this, there are 2 paths here, action layer and observation layer, because critique, remember, what are the 2 inputs of the critiques? Observations and the actions, right? So there needs to be 2 different paths of the input. One path will take in all the observations, the other part will take in all the actions. That's why you see here, the observation input path has 2 neurons. Why? Because you have 2 observations. The action input path in this case has only 1 because you have 1 action. However, the input dimension of the actor will always be equal to the input of the actor. Yes. As many observations as you have. The output will be the number of actions. Actor input will be, yes, actor input will be the dimensionality of your observation space. Actor output will be the dimensionality of your action space. Clear? Okay. Here you notice here that all the in between the activation layers between the layers are ReLU. Okay. You change it. Okay. You can have whatever you want there. Okay, again, you have a continuous deterministic actor. Why? Because it is DDPG, right? However, say if it is SAC, it will be RL continuous stochastic actor. Okay. Then the output will be two numbers basically, the mean and the variance. Here in this one, the output will be one number only, which is a deterministic action. Okay. Clear? Okay. Now coming to this, I should have started the training and then explain this, right? Yeah, okay. Okay. Anyways, I'll start the training now. Okay, for starting the training, you simply have to run the script. No, but I want to show you something even during training. Okay, we'll complete it hopefully. Sorry? Yeah, I know I should have done it 10 minutes ago, but I'm late already. Okay, so now you define your agent options, okay? For every specific algorithm, you have different agent options, okay? So in this one, you're using a DDPG agent. That's why you will use the function RL DDPG agent options, okay? These are not the exhaustive list of all the options. There are many other options that you can play with. If you do not change them, they'll take the default values that MATLAB has given them, okay? So we have what? The sample time, which is the step size basically. Okay. You have the target smoothing factor, discount factor, mini batch size, which is the number of samples that you will take from the experience buffer. Then you have the experience buffer length itself. That is how many samples do you want to actually store. Okay. You can change the discount factor. We did not change the discount factor here. So by default, it will take the default discount factor, which is 0.99. Okay. You can increase the standard deviation for the noise that you have. Okay. You can change the noise as well. You can use the OU noise or the Gaussian noise, whatever you want. Okay. Okay. Learning rate. Remember, learning rate of actor and critique. There was some rule there. What did you have? Right. Yes. So that's why critique learning rate is faster than the actor. Okay. Actor learns at a slower rate. Okay. Okay, then you simply define the RL agent with the actor. Actor here is the actor neural network. Critique is the critique neural network, and agent ops is the agent options. Okay, all this goes to the variable agent. Okay, now coming to the training itself. So now you have to define training options. How do you want to train it? So you define the maximum steps that you have. Sorry, episodes that you have, and then maximum steps per episode. Remember, it is critical for us because we have a terminal condition of 0. So we don't have any terminal condition. Okay. Okay. Now, average window, it is simply just for your understanding of the trend of the reward function. Okay. That doesn't play a significant role in the training itself. Okay. It is for you to understand how the trend of the training is. Okay. Okay. Stop training criteria is when do you want to stop the entire training itself, not the episodic training, but the total training itself. Okay. Now here we have average reward of plus 200, which is an unreal value because this system can never achieve a value of plus 200. Why? Because we simply wanted it to run for all the episodes that we have, all 100 episodes. Okay. If you make it minus 200, then your training might terminate, say, after 20 episodes or maybe after 80 episodes, right? Clear? Okay. This is something important here. Now, save agent criteria. Okay. This is where you define which agents you want to save during the training. Okay. Now, when you're training for 100 episodes, it effectively means that you have 100 different agents, right? Obviously, not all of them will be equally good or equally bad, right? Now, what makes an agent good or bad? Reward, right? In most cases, it is the reward. Therefore, we define the save agent criteria as the episodic reward. Okay. So this way, you're making sure that you save all the agents that accumulate a reward of a certain threshold, above a certain threshold. In this case, we say that the save agent criteria is episode reward and save agent value is minus 300, which means that you will save all the agents, even if it is agent 1 till agent 100, you will save all the agents that have a value higher than minus 300, right? So if your agent gets a value of more than 300 in that episode, it will save. Sorry?
Is less.
Then it will not save. Then it will not save. Okay. So you will see that. Okay. So MATLAB by default, while you're running the training, it will create a folder in the same directory or in the current folder that you are in called saved agents. Okay. And it will keep saving all the agents. Okay. So for 100 episodes, if you have a save agent criteria of all agents, then you will have 100 agents. Agents are nothing but mat files, .mat files, okay? MATLAB data for the basically the neural network of the actor and critic and a few other parameters, okay? But if you do not have any save agent criteria, it will save all 100 agents. And then you have to run all 100 agents to see which is the best one, okay? However, we do not want to do that. We want to have some kind of cutoff, okay? So we say that if any agent gets a reward of more than minus 300, save that agent. Okay, so you will see that at the end of the training, the save agent folder will have less than 100 items. Okay, maybe 70 items, 60, 20. That is that many number of saved agents. Clear? Okay. So this is simply, yeah, you want the training progress and then you can have the verbose for that. Okay. Here, this this command will start the training. Okay. This command will start the training. At the end of the training, when this is done, it will simply display complete the training. Okay. This is a small reset function which says that always initialize. We're making sure that it doesn't always start at the same point. Okay. Otherwise, it may end up memorizing the start and goal points. That is the reason why you have this random here. You see, we have 0.5 plus random, a certain random value. So as to make sure that it will not end up memorizing the start and end positions, right? Even in the velocity, you have a small random number and the position, you have a small random number. So you're basically making sure that you initialize within a certain range and goal is within a certain range. So then it will actually learn how to navigate from the start point to the goal point. We are not controlling the velocity, we are commanding the velocity. This is the reference command. You see? So you simply are concerned about where the UAV will end up at, what position it should end up. So this is telling the reference command to the system. Okay? Velocity will be computed by the RNA agent depending on the position that you have. Clear? That is the reason why you have this only for position. Okay? This is basically a goal position. It is simply, it can be a constant value like 0.5. Okay? And you will always go to the goal of 0.5 only. Okay? But this way, you ensure that it is not always 0.5. It is 0.5 plus some random number. So it can be anywhere in certain vicinity. That way, it will not memorize the goal. You see, it will learn how to move from start to goal position. Clear? Yes. Okay. Now we'll run the training and hope that it is completed before the end of the class. Okay. You simply run the script. Okay. When you run the script, it will open a dialog box called episode manager. Okay. That episode manager will give you the, it's very slow. It will start. Okay. Okay, so the training episode manager will give you the episodic return that you have, okay, in light blue. It is defined by default. That is the light blue curve that you see during training is the episodic reward, okay. Okay, yes. So you see now the training monitor opens. And also you don't have to create a folder for save agents. MATLAB will do it. MATLAB will create a directory called saved agents in the same current folder that you are in, and it will save all the agents that are above a certain threshold. Okay? Okay. I will tell you that. I will tell you that. Sure. Now, while that how to select the agent that you is good. Okay? So when this training is good, you will see that it will have a curve like this. Okay, it will have a curve like this. This will be your training curve. Okay, what you have to do is simply all the agents. So this is your threshold of say 300. This is minus 300. So all agents that have values higher than this will be same. All these agents will be same. Okay. Now, a good way would be to, if you're very sure about the threshold, then what you do is you will have obviously a limited number of agents. Okay. You can simply create a for loop to run the simulation for all the agents. Okay. And then visualize them and then pick the best one. However, that is slightly complicated. So for ease of understanding, what you can do is zoom into this part. I'll show you when the training is done. You will have an option of zooming into the train episodic reward part. Okay. So you take after zooming, you will see you can numerically see which agent has the highest value. Okay. So you simply take that agent. Every point in that train curve will have a label, and that label will correspond to the age saved agent number. Let's say agent 78, agent 62. Okay. You simply take that agent and run your simulation. Let's start an agent perform this. Right? I'll show you how we do that as well. Don't worry about it. Okay, training is relatively quick. In 3-4 minutes, we have. Yes, what do you want me to explain?
Explain to the faculty, we need to meet.
Whatever you want to do. You explain what you do. Okay? Look, now for visualization of results, you can do it using two ways. Okay. One is through a scope block. There's a block called scope block in Simulink. You can simply put a scope block here and then log the velocity and the position. Okay. The other one would be to have a workspace block. Okay. That way you will send the what do you say, the velocities and positions, that is z and z dot, from Simulink to MATLAB. Okay, because here when you run something in here in Simulink, that might not directly show in the, well, that will actually, but for ease of access, you use a two workspace block. Okay, and then you send whatever signals you want to MATLAB workspace. And once you have it in MATLAB workspace, you can simply use a plot function and plot the graph that you have. From that graph, you can there are tools within the plot function that you can select the peak value, the lowest value, the steady state value. From that, you will get the performance characteristics or the performance metrics. Right? Clear? I did a training earlier. I will show you the results that I got for that. Okay. These are the results from an earlier training episode that I did. Okay. You will see that the reward oscillates a little bit and then it converges. This is the zero value and then it moves towards that and basically it converges. You see, it doesn't oscillate much now. An earlier training episode that I did. Okay. And I have it saved. I'll run the agents from this one. I already have saved agents, okay, from a previous training instance. So you see all these agents are saved. There are 75 agents that are saved out of 300, out of 100. Okay. Now let me run that file as well. You will go to the save agent folder. Okay. You will go to agent 82. Okay. And you will drag and drop that thing in the command window. Okay. When you do that, your workspace agent will be updated now. Okay. Now you have the Simulink file. I'll put a scope block. Okay. So we simply want, okay, we want the position, right? Okay, position. You open the scope block and this is painfully slow. Okay, simply click run simulation now. Yeah, you can even do that. You can even do that. Just I'll show you. Yeah. Okay, now we do get the actual results that we want, okay? I was making a small mistake. So what I did here, in this RL agent, the agent object is the file that you want to load, the agent that you want to load, right? So here you see the name of the saved agent is actually not agent. It is saved underscore agent. Okay, so that is what the mistake I was making. Here. Okay, let me clear the workspace. I'll clear the workspace. Okay. Now if I open, okay, I'll do it again. Now if I'm dragging and dropping any agent, say agent, whatever agent this is, agent 98, for example. Okay, if I drag and drop that agent here, you see what is the name of the agent now? Saved underscore agent. Okay, so your MATLAB block here for RL agent should have that name, saved underscore agent. Earlier we had the name called agent, right? Which is something that we were using during training. So the result that we were getting was for the last trained agent. Okay. Okay, so listen. First, after your training is done, clear your workspace. Okay. You don't have anything in the workspace, right? Now you go to this reward function curve. Okay. And using the method that I showed you, you will find the agent that has the highest numerical value. Okay. Assume in this case that it is agent 96, for example. Okay. So you will go to the save agent file. You will go to the save agent file. Okay. And you will search for agent 96. Okay. Then you see here, your workspace is empty now. Everyone, please pay attention here very carefully. Very carefully. Okay. Agent 96, you are assuming is your best performing agent with the highest reward. Go to that directory, select agent 96. Here, make sure that your workspace is empty. Okay. Select this agent 96, drag and drop it in the command window. Okay. This will load the saved agent. Okay. Here, the name of your agent is saved underscore agent. Okay. So make sure that your Simulink model RL block has the same name. It should have the name saved agent. Okay, by default, it will have the name agent only, which is the name that we are using during training.
So after the training, when the training,
Yes. To whatever the name that agent is. Yes. In this case, it happens to be saved underscore agent. Okay, you can simply reload them. Those are parameters. That's why if you see here, I will reload it now. Okay. You see here, that's why I created it in a subsection. So all you have to do is run the subsection. It will again, you see now your workspace is populated. So you have all the parameters now. Clear? 100%?
sorry, I'm not seeing from the screen. What other part other than safety?
Oh, those are the physical parameters, the gravity, mass, kV, saved agent result. So basically that will save the numerical reward for each episode, which will help you plot the training curve if you want to plot. Okay. Okay. Now with that here, what you will do is you will open this last agents. Yes. No. Here, if you see the training that I did earlier, it converges around 50 episodes and it doesn't change much. Right. So therefore, that's the reason why I'm taking an agent towards the later part, right? 80, something around that. Okay. Now let's try again with say agent 82 maybe. Okay. Yeah, both of them are same. So basically that is the velocity. So you see the velocity also does converge to 0 and the velocity is not very oscillating. You can see from here, right? It goes to a peak and then it quickly goes to 0 and position also stabilizes, right? There might be a steady state error, obviously. You can work on it, but you get the idea now, okay? Now to get the performance parameters from this one, okay? So in MATLAB, you have this tool here. You see cursor measurements, okay? Click on those cursor measurements. Okay. So okay, you have the cursor measurements. Now here you can select for what value you want. Like the first one is INTZ. It will be in that order, by the way. Okay. First one is for the first row, second for the second row, third for the third row. Okay. So select INTZ here. And if you move this, okay, if you move this here on the left side, you will see time. So now your cursor 1 is corresponding to a time of 7.16 seconds and the value is 1.112. Okay. That is how you get the values. And if you simply select say RL agent, now you are in this block, third one. So this will give you the velocity here. So now at 3.81 seconds, your velocity is 0.168. Okay. Clear? So from this, you will get the performance metrics. Performance metrics are nothing but say the peak value and the steady state value. Okay. And the steady state error. You will compare these three things. That's it. For velocity, you will write the peak value and how long does it take for it to reach zero velocity, implying be stable. Clear? Okay. Also, MATLAB has something called peak measurement. So you see this option here, last one in that cursor measurement. If you click that, it will directly find you the peak values, right? You don't have to manually move your cursor to select the peak values.